In today's lecture, we're discussing how we can use the dynamics equations of motion that we derived last week in order to control a robotic system. In the last week's video segments, we looked at three different methods in how we can derive the equations of motion in joint space as a function of q, q dot, and q double dot. In particular, we looked at Newton-Euler, projected Newton-Euler, and Lagrange 2. And in the end, it's really up to you and up to the problem which of them you think is most appropriate to be used. I personally use very often projected Newton-Euler simply because it's, in my eyes, very intuitive and gives you direct access to manipulate equations of motion if you have to. So what these methods end up in is in a description that looks the following way. We have mass matrix times acceleration plus Coriolis centrifugal part plus gravity part equals to the actuation torque. Now what is new and what will be used also in this class is in case you have external forces acting on a system, in that case we call it contact force, they interact through a Jacobi at that point where they act with the Jacobi transposed onto our equations of motion. Now today we're gonna change causality. Instead of giving you a torque and you tell me how the system is moving as we need it during a simulation, revert now and we start from a desired motion that we want to achieve and we want to figure out what is the required joint torque in order to drive the system in the planned manner. Recap, I have here the two videos that we have seen already earlier. You see on the left hand side a kinematically controlled robot arm which is moving an object along a predefined trajectory, and it's moving the object independent whether it's carrying like a 200-gram payload or a 200-kilogram payload. This system is kinematically controlled, is built and controlled just as stiff as possible. Then we're talking about position control systems. In contrast to that, on the right hand side, you see a video of DLR with their robot arms which have integrated torque sensing, which can be controlled in a fully dynamic manner. So they're not only able to regulate a position, but they're also able to regulate an interaction with their environment, and hence to compliantly interact with human collaborators. These systems, so-called torque controllable system, require a full system dynamics description in order to achieve a control performance as we see it in these videos. Now, if you look a little more into details in how such a robot arm is set up, we can identify three components. We have the first part, which is the actuator control, which essentially is the electronics that drive our motors, where we produce a voltage and a current that drive the motor and gear system, which we summarize over actuators. That gives a torque that acts on our multi-body dynamics, which then gives an output of the position, velocity, and acceleration. Now what you see here on the left, this part, this is all on joint level, while this multi-body dynamics is where the coupling happens between the multi-body system. Now if you close the loop, if you make this system controlled, what we're doing is we're measuring the state and we're producing an actuator control input in order to drive it. If you look at the classical position controlled robot arm, then the setup looks the following way. You have a position sensor which measures the state, so Q and Q dot, and feeds that back into a high gain PID feedback loop where we get the desired position and velocity and produce a command that goes to the actuator through PID feedbacks. If you look at the closed loop behavior of that robot, you have the boundaries that is on the input side, we have Q and Q dot desired, and on the output we have the corresponding state. So we have a direct mapping between in and output, which is in the ideal world almost identity until very, very high frequencies. That means you want to achieve a closed loop feedback system which makes sure that you're not really taking care of the robot dynamics, that these high gains in the PID controller ensure very good joint level tracking independent of the disturbances. So if I have here an external disturbance acting on my robot, for example, if I collide with something, that this is immediately measured and tracked over the high gain PID loop. In other words, such a robot is not really able to control force. The only ability to control force is if we assume the environment to be compliant. So if you have an environment which is rigid and then we have a compliant element in between, now if I'm controlling the motion of the robot along a predefined trajectory and we have a defined compliance, then of course the force acting on the wall can be controlled through the motion at the end effector, but we cannot directly control a force with such a setup. Now the setup looks slightly different if you have joint level feedback control of torques. What we're doing now is that we are integrating a torque sensor. We're measuring the torque and we're trying with our actuator control to track a desired torque, this tau star, as well as possible. And what we want to achieve is that we have an ideal mapping between the desired torque that is commanded to the actuator and the torque that the actuator actually produces on our multi-body dynamic system. With this integrated force feedback, we can actively regulate the system dynamics. We can do model-based load compensation, and we can also actively regulate interaction forces. So assume that this robot has to produce an active force onto our environment. What we can do is we can take this planned force that we want to achieve. We do a mapping with a controller from the force that we want to produce at the end effector to the joint torques, and then give this directly as an input to our actuator controller. Now, if you look at modern robotic arms, in particular the ones that are collaborating with human, they all have integrated force or torque sensors. This allows them to do dynamic control, to regulate the interaction force with the environment, and hence to safely collaborate with humans. What you see here on the right hand side is a classical setup of such a robot joint with an integrated torque sensors. So what this has is, on one side you have the control electronics, then you have a motor and a gear setup, and then at the output you have a torque sensor, which in the end measures the joint torque that is acting on the following link. One example of such a robot which has recently caught a lot of attention on the market is Franka Emika. This is a German company that has been growing quite a bit over the last couple of years and who's making collaborative robot arms, so arms that can not only precisely regulate end effector positions and velocity, but which is able to, first of all, be guided by a human, so interact with humans, but then also actively regulate the interaction force at the contact point. This is very important if you have to bring things together. For example, if you have to put a key into a lock, if you have to place now this mobile cell phone from one position to another, and when you don't have exact positions of where this thing should go, and you don't want to control it with the infinite stiffness to sub-millimeter precision, you can just control it to the approximate location, and then, as a human is doing, like bring things together, let you guide by the form fit that this part has, and by that assemble tools like here, or assemble robots like here, the robot assembling the robot itself.